Hey, what's up guys? Welcome back to Python 101, and today we're on week 24, part 1. So, yay, good job. Let me open up my thing. So, today we don't have a lot of slides, but we do have a lot of work. So, let me open up Anaconda. And because this is on my other computer, so it's gonna open on the Microsoft Edge. But either way, let me start sharing my screen. So, all right, week 24, part 1. We're gonna start talking about custom widgets now, and today we're gonna explore this mathematical system of equations called the Lorentz system of differential equations. The black thing is popping up. That's my Anaconda Navigator opening up, and yeah, I'm gonna open it up once it. Okay, so it's up. Launch Jupyter Notebook. All right. So this is the Lorentz system of differential equations. If you don't know much about it, you can. Well, let's see what am I talking about? You can just search it up. Now, this is the thing. So x equals blah 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 blah, all that Greek stuff, Greek number stuff. Now, let's see, my thing's open. Let me open a new Python 3 and let me get my keyboard. All right, so let's call it Python 101 week 24 part 1. Yeah, it's part 1. Let me close out this thing. I don't need it. All right, no. This is one of the classic systems in nonlinear differential equations. It exhibits a range of different behaviors as parameters. This, and this are varied. First of all, when you see this math stuff, you know that you're gonna have to do some importing, and this is what you have to import. That's a lot of stuff, I know. But hey, you could just pause it here and then just do this. Actually, let me just import them one at a time. So this. Let's get these two in first. Now let's get the rest of them in. Oops. And if you want to know more about all that, IPython, NumPy, Matplotlib, and SciPy, then, well, I have some. First of all, you can go to the official Python documentary stuff. So it's python.org, and I'm gonna include the links in the description on YouTube. So, yeah, I'm gonna post there first, just in case, WeChat, it takes so long to post. Either way, let's start. So we're gonna compute the trajectories of the equation, and we're gonna plot the result. So we define a function that can integrate the differential equations numerically and then plot the solution. So that's where matplotlib comes in. It just plots things. This function has arguments that control the parameters of the differential equation. These are the parameters. And the numerical integration of n, max underscore time, and the visualization, which is the angle. Now, I told you there wasn't a lot of slides, but there's a lot of work. So we're going to define something called solving the Lorentz. And we're going to set n equal to 10. Angle, we're going to keep the angle at 0.0. We're going to have the maximum time, underscore time actually. And that's going to be equal to 4.0. So make sure it's in decimals. So that's where scientific, I mean, not scientific notation. That's where the thing where you get the most important places in the decimals in physics comes in. Anyway, just keep it to the tenths. No, even if you don't have a zero. So, and then there's sigma. So sigma is the first. So sigma is this little thing here, I think. I hope. Wait. So this is sigma. This is beta, obviously. And this is rho. Yeah, this is rho. Okay, these are, I told you, these are all Greek stuff. I'm not Greek. I don't speak Greek. I don't eat Greek. I do eat Greek salad, but I don't have Greek alphabet, okay? So, okay. So 10.0. And then beta is gonna, let's set beta as 8.0 over 3. Finally, let's set rho as 28.0. And that's just some of the parameters of our, well, that's all of the parameters, but of our thing. Now let's define it. So we're gonna define the figure equals to plt dot, so you can see that matplotlib plot dot figure, and then we're gonna have this inside. Now we're gonna have the ax equals to the fig dot add axis. So add ax, this is for the axes. We're gonna have this. Let's add this while we're at it, and inside we add this list-like thing. So 0, 0, 1, 1, and this the inside of the axes is kind of like a tuple thing. So it's like a tuple thing, and yeah, you just do the projection as 3D. Oops. Now, I'm gonna set the axis as off, and while we're at it, we're gonna prepare the axis limits. So ax dot set underscore x dot limit, or just xlim. Let's put a coordinate inside, so negative 25, 25. I'm just gonna copy and paste this, because why not? All right, so we got these numbers. Now, this is y, z. Keep it as 35, 35, 5, 55. Now, inside the solve Lorentz, we're gonna define something that's gonna derive the Lorentz. So we're gonna just call it derivative. Yeah, so it's gonna have some of the same properties, but here we're just gonna have x underscore y underscore z t0 sigma equals sigma, and beta equals beta, and rho equals rho. So now that we have our parameters defined, so x, y, z is our 3D coordinates, sigma and beta and rho are things, and yeah. Oops, I accidentally ran it instead of defining it. So here we're gonna compute the time derivative of a Lorentz system. So x, y, z is gonna be equal to x underscore y underscore z. We're gonna return sigma times, so you can find this if you do some research on the Lorentz equation and stuff. You'll find an equation And let me separate these into threes first. Okay, so we're gonna have sigma times y minus x times, finish that thing here, x times rho minus z, and x times y minus beta times z. Now, don't go yet. I keep accidentally pressing shift enter when it's just supposed to be regular enter. So now let me just share this. Now we're gonna start choosing random points and uniformly distribute from -15 to 15. So that's our x and negative x, as you saw from our previous thing. And yeah, so there seems to be a problem. Let me try to, there's not really a problem. Either way, let me okay, so as I was saying, we're gonna keep doing the inner definition of the Lorentz derivative. So we're gonna do np.random.seed. We're gonna have 1 inside, and then we're gonna have x0 equals -15. And once again, this is advanced part. This is introduction to GUIs. And GUIs are those, things you use for loading screens, and you can even use those for, like, we're doing scientific stuff, and this is the advanced scientific, well, intermediate scientific stuff. And when I'm done with Python 101, I'm gonna start Python 201, and that's basically just on data and stuff like that. So anyway, let's go on. Negative plus 30 times np.random.random twice. We're gonna do that twice, and then have n and 3 inside. Now, what we're gonna do is solve for the trajectories. Actually, you know what? I'm gonna write the steps in here. So as comments. So we're gonna prepare the axes limits here. Well, we already did it. And here we're gonna, like I said, we are going to choose random starting points uniformly distributed from -15 to 15. We're gonna scroll it up. All right. Now, like I said, we were gonna solve for the trajectories. All right, so t equals np numpy dot lin space 0 max time and comma max underscore time. Don't make those mistakes because they can get really messy. And now we're gonna have to int the 250 times the maximum amount of time. Now we're gonna have x underscore t equal to np dot as array, and we're gonna have kind of a list thing inside. So we're gonna integrate dot odd int. We're gonna have Lorentz underscore deriv x0i, x01, x0i, t for xoi in x0. I know that was a lot to take in, but let's take a chill pill. First, we need to make sure the things here are aligned, so you can see that this is green, so this is aligned. What about this? Is this aligned? Yes, this is aligned. Okay, cool. Okay, all right. Now we're gonna choose a different color for each trajectory. So this is the artsy part. So colors equals plt.com, cm dot jet, have np dot linspace, and we're gonna have 0, 1, n. Now we're gonna have this in, and here we're gonna have for I in range n, we're gonna have x, y, z equal to x underscore t, and then we're gonna have this list, and then we're gonna slice it with this, and then we're gonna have dot t. So may look complicated, but you'll see in a sec. So lines equal to x dot plot, and we're gonna have x, y, z, and we're gonna have this in between, this thing in between, and then c equals colors, and then for each I. Now we're gonna have underscore equals plot dot set p lines, and then line width equal to. Despite all these complicated things, remember this is still widgets, okay? Those hefty widgets. So ax.view underscore init, don't worry, we're almost done. We're gonna have 30 and then angle. Now we're gonna have underscore equals plt.show, and we're gonna do that. Now we're gonna return t and x underscore t. Generator must be parenthesized if not sole argument. Let's see, x01, I think it's xt, yes, this one. All right, folks, I'll be back in a second, right after I figure out what's wrong. Okay, so remember how I said earlier that if you forget one parentheses, one tiny, small, yet needed parentheses, then something's gonna be wrong. Well, yeah, that's what happened here. I forgot this parentheses, and you know, it's mismatched, and things happen. Now, when I run it, it doesn't give me a problem. Let's call a function once to view the solutions. For the set of parameters, we see the trajectory swirling around 2 points, and the 2 points are called attractors. T, comma x underscore t, solve underscore Lorenz. We're gonna have angle equal to 0, and then n equal to 10. Okay, there we go. There's our beautiful picture that Python produced. And you see those 2 points here and here. Well, like I said, these were called attractors, and you know, if you move that into 30, and yeah, so you can experiment around with that. But like I said, before you do this, I suggest that you really read the Python documents on NumPy, Matplotlib, SciPy, yeah, let's see what else, and that stuff I put on there. So like I said, it's gonna be on my YouTube, and guess what? It's a great time to show it, I guess. It's gonna be a good time to show it. So you are a little child who is wandering around, and you saw that my videos of Python have been deleted. And yes, that is true, because I got a new YouTube channel, and all you have to do is search up Python with key space thing, and you'll see that here I am. And I got some new background, or like thumbnails for these videos. And yes, now a lot of people know, so I'm just putting it out there that I've got this new one. Yeah, so yeah. Anyway, let's keep going. So, and then here you can also change this into 100, and then you see it gets way denser. Now, we're gonna be using Python's interactive function. We can now explore how the trajectories behave as we change the various parameters. So we can set W equal to interactive solve underscore Lorenz. We're gonna have angle equal to 0.0, sure, or you could just point 0 point. And then you can put comma here, 360 point. That's funny because that's how Python works. N equals to 0.50, and sigma is going to be equal to 0.0, comma 50.0. Now we're gonna RHO equals 0.0. Oops. Yes. 0.0, and then we're gonna have 50.0. Yes. And then we're gonna display W, and then yeah. All right, so as you can see, we can control this, and then whoop, whoop. Okay, yeah. You can't go below the maximum or minimum. Yeah, there we go. That's why it might give you a problem. And then RHO, yeah, beta, sigma, next time. All right, so you get the point. You can experiment around with that, but I'll keep going because life is short. Now, the object returned by interactive is a widget object, and it has attributes that contain the current result and arguments. So if we do, let me move my mouse, x underscore t equals w dot result, and we can do k dot coords, and you will see that this is all our information that I put on here so far, and some of them are exaggerated, some of them aren't. Now, after interacting with the system, we can take the result and perform further computations. In this case, we can compute the average positions in x, y, and z. So if we just do x, y, z underscore average equals x underscore t dot mean, and then axis we just set it as 1, and then we could do x, y, z dot average underscore average dot shape. And here it is. That's the coordinates. Creating histograms of the average positions across different trajectories show that on average the trajectories swirl about the attractors. So yeah, these will look different from whatever you're using, and yeah, so let's do a histogram. So plt.hist, and we'll have x, y, z, average. We're gonna have a list slicing here. plt.hist, oh no, title, we're gonna set the title because, you know, why not? And then we're gonna set the, we're gonna call it average xt. Oops, there we go. So here it is, and as you can see, the kind of money sign, it just makes it tilted a bit, you know, stuff like that. And that's our histogram. And once again, it depends on how you did it, because mine looks like this. I just did this. Mine looks like this. And if we do plt.hist, and then we do average xyz z tab, it's gonna complete it for me. This 0, this, oh wait, 1. We're gonna have plt dot title. And how about I just, and then, you know, it does the same thing. But you know, it depends on what you did, because mine is like to the maximum. It's gonna be the same, but you know, if I change it, it's gonna be different. So everyone, thank you for attending my lecture, and I'll see you next time. Bye.